Mars has always fascinated us, a mysterious red beacon in the sky. What if it holds the key to our future? From towering volcanoes to ancient river valleys, Mars hides stories waiting to be told. Could we find life there? What challenges would we face living on this distant world? Mars isn't just a planet, it's a puzzle with pieces scattered across time and space. Hold your breath as we peel back the layers of the red planet, revealing its wonders and the tantalizing possibility of human colonization. This isn't science fiction. It's our next giant leap. Mars, often called the Red Planet, is the fourth planet from the Sun and the second smallest in our solar system. Its reddish appearance, due to iron oxide, rust, on its surface, has fascinated humans for centuries. Mars has a diameter of about 6,779 kilometers, roughly half the size of Earth, with a surface area comparable to Earth's landmass. Despite its smaller size, Mars' landscape is diverse, featuring the tallest volcano in the solar system, Olympus Mons, and the deepest canyon, Valles Marineris. Mars has a thin atmosphere composed mainly of carbon dioxide, with traces of nitrogen and argon. This atmosphere is not sufficient to support human life, contributing to extreme temperature variations from around -125 degrees Celsius at the poles during winter to 20 degrees C at the equator during summer. The planet's gravity is about 38% that of Earth, which presents both challenges and opportunities for human exploration and potential colonization. Historically, Mars has been a focal point of numerous scientific missions. From the early flybys by Mariner 4 in 1965 to the sophisticated rovers like Curiosity and Perseverance exploring its surface today, Mars continues to be a prime candidate for studying the potential for life beyond Earth and understanding the planet's history and geology. Mars is a planet of striking geological diversity and complexity. One of its most prominent features is Olympus Mons, the tallest volcano in the solar system, standing at approximately 22 kilometers high, nearly 3 times the height of Mount Everest. This shield volcano indicates that Mars once had significant volcanic activity. Another remarkable geological feature is Valles Marineris, a canyon system stretching over 4,000 kilometers and reaching depths of up to 7 kilometers. This vast canyon dwarfs the Grand Canyon and offers insights into the tectonic and erosional processes that have shaped Mars. The planet's surface is also marked by expansive plains like the Tharsis Volcanic Plateau, home to several large volcanoes. In contrast, the Hellas Planitia is one of the largest impact craters in the solar system, spanning about 2,300 kilometers in diameter and plunging 7 kilometers deep. Mars's surface bears evidence of ancient water flow, with dried-up river valleys and outflow channels suggesting that liquid water once sculpted the landscape. Features like the delta in Jezero crater, where the Perseverance rover is currently exploring, highlight past aqueous activity. Additionally, Mars' polar ice caps, composed of water and carbon dioxide ice, expand and contract with the changing seasons, indicating dynamic climatic processes. These geological features not only provide clues about Mars's past, but also guide current and future exploration missions in the search for signs of past life and the planet's habitability. The history of Mars exploration is a tale of human curiosity and technological advancement. It began in earnest with the Mariner 4 mission in 1965, which provided the first close-up images of Mars, revealing a cratered, moon-like surface. This marked the beginning of a new era of planetary exploration. Subsequent missions, such as Mariner 6 and 7, continued to map the Martian surface, while Mariner 9 in 1971 became the first spacecraft to orbit another planet, offering detailed images of the vast canyons and volcanoes on Mars. The Viking 1 and Viking 2 missions in 1976 took the exploration further by landing on the Martian surface, conducting experiments and searching for signs of life, though no conclusive evidence was found. The 1990s and 2000s saw a renaissance in Mars exploration. The Mars Pathfinder mission in 1997, with its Sojourner rover, demonstrated the feasibility of robotic rovers on Mars. This success was followed by the Mars exploration rovers Spirit and Opportunity in 2004, which greatly expanded our understanding of the planet's geology and the presence of water. The 2010S brought advanced missions like the Curiosity rover in 2012, which discovered ancient habitable environments, and the Mars Reconnaissance Orbiter, providing high-resolution mapping. The recent Perseverance rover, which landed in 2021, is equipped with advanced tools to search for signs of past life and collect samples for future return to Earth. Each mission builds on the successes and lessons of its predecessors, continually advancing our knowledge and bringing us closer to the goal of human exploration of Mars. Mars rovers and landers are pivotal in our quest to understand the Red Planet. These robotic explorers have revolutionized our knowledge of Mars, providing detailed data and vivid imagery of its surface and atmosphere. The journey began with the Viking 1 and Viking 2 missions in 1976, the first successful landers on Mars. These stationary landers conducted experiments searching for signs of life and provided valuable data on Martian soil and weather. In 1997, the Mars Pathfinder mission introduced the Sojourner rover, the first to traverse the Martian surface. Sojourner's successful operation demonstrated the feasibility of mobile exploration on Mars, setting the stage for more sophisticated rovers. The Mars exploration rovers, Spirit and Opportunity, landed in 2004 and far exceeded their planned 90-day missions. They explored vast distances, analyzed rock and soil samples, and found evidence of past water activity. Opportunity's mission lasted nearly 15 years, marking a significant milestone in Martian exploration. Curiosity, landing in 2012, took a leap forward with its advanced laboratory on wheels. It discovered ancient habitable environments and provided insights into Mars climate and geology. In 2018, InSight, a stationary lander, began studying Mars' interior using a seismometer and heat probe, offering clues about the planet's formation. Perseverance, which landed in 2021, carries cutting-edge instruments to search for signs of past life and collect samples for future return to Earth. It also deployed Ingenuity, a small helicopter, marking the first powered flight on another planet. These rovers and landers are essential in unraveling Mars' mysteries, paving the way for future human missions and potential colonization. The search for water on Mars has been a central focus of planetary science, driven by its implications for past and potential life. Evidence suggests that liquid water once flowed on the Martian surface, significantly shaping its landscape. Initial clues came from orbiters like Mars Global Surveyor and Mars Odyssey, which detected signs of water ice and ancient river valleys. High-resolution images from the Mars Reconnaissance Orbiter revealed intricate networks of dried-up river channels and deltas, indicating that water once carved its way through the planet's terrain. In 2008, the Phoenix lander made a groundbreaking discovery by confirming the presence of water ice just below the Martian surface at its landing site near the North Pole. This was a pivotal moment, providing direct evidence of water on Mars. Further exploration by the Curiosity rover found ancient lakebeds and minerals that only form in the presence of water, suggesting that Mars had liquid water and a more temperate climate billions of years ago. These findings point to the possibility that Mars could have supported microbial life in its distant past. In recent years, radar data from the European Space Agency's Mars Express mission revealed the presence of subsurface lakes of liquid water beneath the planet's south polar ice cap. This discovery has sparked significant interest as it suggests that liquid water could still exist on Mars today, albeit in a very salty form. The continuous study of water on Mars helps scientists understand the planet's climate history and its potential for life, guiding future missions in the search for signs of past or present microbial life and informing the prospects of human colonization. Mars' atmosphere is thin and composed primarily of carbon dioxide, 95.3%, with traces of nitrogen, 2.7%, argon, 1.6%, and a small amount of oxygen and water vapor. This composition is vastly different from Earth's, making the Martian atmosphere inhospitable for human life as we know it. One of the most significant aspects of Mars's atmosphere is its low pressure, which is less than 1% of Earth's at sea level. This low pressure means that liquid water cannot exist on the surface for long, as it quickly evaporates or freezes. The thin atmosphere also contributes to extreme temperature fluctuations, with daytime temperatures at the equator reaching up to 20 degrees C, 68 degrees F, and nighttime temperatures plunging to -73 degrees Celsius, 100 degrees F. Mars' atmosphere plays a crucial role in its weather and climate. It is responsible for the planet's iconic dust storms, which can encompass the entire planet and last for weeks. These storms are driven by the sun heating the Martian surface, causing air to rise and creating powerful winds that lift dust into the atmosphere. The atmosphere's composition and pressure also affect the potential for future human exploration and colonization. Breathing on Mars would require life support systems to provide oxygen and regulate pressure. Additionally, the lack of a strong magnetic field means that Mars's atmosphere offers little protection from harmful solar and cosmic radiation, posing significant challenges for long-term human habitation. Recent missions, like NASA's MAVEN, Mars Atmosphere and Volatile Evolution, Orbiter, are studying the Martian atmosphere's upper layers and how it interacts with solar wind. Understanding these interactions helps scientists learn how Mars's atmosphere has evolved over time, shedding light on the planet's history and its potential to support life. Mars experiences a variety of weather and climate patterns that are distinct from those on Earth due to its thin atmosphere and distance from the Sun. The Martian climate is characterized by cold temperatures, with an average surface temperature of about -63 degrees Celsius, -81 degrees Fahrenheit. However, temperatures can vary widely, from a relatively warm 20 degrees Celsius, 68 degrees Fahrenheit, at the equator during summer to a frigid -125 degrees Celsius, 193 degree F, at the poles during winter. Seasonal changes on Mars are driven by its axial tilt of about 25 degrees, similar to Earth's 23.5 degrees, leading to distinct seasons. These seasons, however, are nearly twice as long due to Mars's longer orbital period around the Sun, which takes about 687 Earth days. One of the most dramatic weather phenomena on Mars is its dust storms. These storms can be regional, or in some cases engulf the entire planet, reducing sunlight and significantly impacting temperatures. The largest dust storms can last for weeks and have been known to affect rover operations and solar energy collection. The Martian atmosphere, composed mostly of carbon dioxide, is also responsible for thin clouds of water ice and dry ice, frozen carbon dioxide, which can form in the atmosphere and on the surface. During winter, the polar ice caps expand as temperatures drop, and carbon dioxide from the atmosphere freezes and deposits as dry ice. In spring, these caps recede as the dry ice sublimates back into the atmosphere. The thin atmosphere leads to low air pressure, meaning that liquid water cannot exist on the surface for extended periods. Water ice is present at the poles and beneath the surface, and transient streaks observed on crater walls suggest that salty liquid water might occasionally flow. Understanding Mars' weather and climate is crucial for future human exploration, as it influences landing site selection, habitat design, and the planning of surface operations. Studies continue to reveal the planet's dynamic climate and its implications for the possibility of past or present life on Mars. Terraforming Mars refers to the hypothetical process of altering its environment to make it habitable for humans. This ambitious idea involves transforming the planet's atmosphere, temperature, and surface conditions to support Earth-like life. One major goal of terraforming Mars is to thicken its atmosphere, primarily composed of carbon dioxide. A thicker atmosphere would increase surface pressure, allowing liquid water to exist. This could be achieved by releasing greenhouse gases to trap heat, thus warming the planet. Methods proposed include using factories to produce gases like carbon dioxide and methane, or redirecting ammonia-rich asteroids to impact Mars, releasing their gases upon collision. Another aspect of terraforming is increasing the planet's temperature. Mars' average temperature is around -63 degrees Celsius, 81 degree F. By increasing atmospheric pressure and using greenhouse gases, scientists aim to create a more stable and warmer environment. Mirrors placed in orbit to reflect sunlight onto the surface have also been suggested as a means to heat specific areas of the planet. Water is essential for life, and one aspect of terraforming Mars involves creating stable bodies of liquid water. This could involve melting the polar ice caps or extracting water from subsurface ice deposits. Achieving this would create rivers, lakes, and potentially seas, fostering a more Earth-like hydrological cycle. Introducing Earth-based plants and microorganisms could play a role in converting carbon dioxide into oxygen through photosynthesis, gradually making the atmosphere breathable for humans. Lichens and cyanobacteria are potential candidates for initial introduction, as they can survive in harsh conditions and contribute to soil formation. Terraforming Mars presents immense technological, ethical, and environmental challenges. It would require massive resources, advanced technology, and a deep understanding of the Martian environment. Additionally, ethical considerations regarding the potential impact on any existing Martian ecosystems must be addressed. While terraforming Mars remains theoretical, it continues to inspire scientific and public imagination as a potential future for humanity beyond Earth. The potential for life on Mars has been a central question in planetary science, driving numerous missions and research endeavors. Mars' environment today is harsh, with cold temperatures, a thin atmosphere, and high radiation levels. However, evidence suggests that conditions may have been more favorable for life in the past. Mars' ancient water features, such as dried-up riverbeds, lake beds, and minerals formed in the presence of water, indicate that liquid water was once abundant. Gale Crater, explored by the Curiosity rover, and Jezero Crater, the landing site of the Perseverance rover, both show signs of ancient water activity, suggesting that Mars once had a climate that could support life. Extremophiles on Earth, organisms that thrive in extreme conditions, provide clues to the types of life that could potentially exist on Mars. Microbes that live in acidic, saline, or cold environments on Earth could have analogs on Mars, especially if similar niches exist. Methane detection in Mars' atmosphere has sparked interest, as on Earth, methane is often produced by biological processes. While geological processes can also produce methane, its presence on Mars raises the possibility of subsurface microbial life. Seasonal variations in methane levels detected by Mars orbiters and rovers suggest an active source, potentially linked to biological activity. The search for life on Mars involves looking for biosignatures or signs of past or present life. The Perseverance rover is equipped with instruments to detect organic molecules and will collect samples to be returned to Earth for detailed analysis. Subsurface exploration is also crucial, as life could exist below the surface where it is shielded from harsh surface conditions. Future missions aim to drill into the Martian subsurface to search for signs of microbial life. While definitive evidence of life on Mars has yet to be found, the quest continues to inspire scientific research and exploration, driven by the tantalizing possibility that life might exist beyond Earth. Human missions to Mars represent one of the most ambitious and challenging endeavors in space exploration. The goal is to send astronauts to Mars, conduct scientific research, and eventually establish a human presence on the Red Planet. A key aspect of human missions to Mars is the development of advanced spacecraft capable of carrying astronauts safely across the vast distance between Earth and Mars, which can vary from 54.6 million kilometers to over 400 million kilometers. NASA's Artemis program and SpaceX's Starship are among the leading efforts to design and build the necessary spacecraft. Once on Mars, astronauts will face a host of challenges. The thin atmosphere, composed mostly of carbon dioxide, means that habitats must be pressurized and equipped with life support systems to provide breathable air. Temperatures can drop to minus 125 degrees Celsius, 193 degree F at night, requiring well-insulated and heated habitats. Radiation exposure is a significant concern due to Mars's lack of a protective magnetic field and thin atmosphere. Long-term missions will need shielding solutions, such as habitats covered with Martian soil or built within natural features like lava tubes. Another critical aspect is the provision of food and water. Growing food on Mars using hydroponics or aeroponics will be essential for long-term sustainability. Water can be extracted from subsurface ice or the atmosphere. Energy sources for human missions will likely include solar panels and possibly nuclear reactors, providing reliable power for habitats, research equipment, and vehicles. In addition to technological challenges, human missions to Mars will require addressing the psychological and health impacts of long-duration space travel. Astronauts will need robust mental health support and medical care capabilities. International collaboration will play a vital role in human missions to Mars, pooling resources, expertise, and funding from various space agencies and private companies. Overall, human missions to Mars represent a monumental step in space exploration, promising to expand our knowledge of the red planet, search for signs of past life, and lay the groundwork for future human colonization. Living on Mars presents numerous challenges due to its harsh and alien environment. The thin atmosphere, extreme temperatures, and high radiation levels are just a few of the obstacles that must be overcome to establish a sustainable human presence. The Martian atmosphere is composed mostly of carbon dioxide and has less than 1% of Earth's atmospheric pressure, making it unbreathable for humans. Habitats must be pressurized and equipped with life support systems to provide oxygen and remove carbon dioxide. This requires advanced technology to create a stable and livable environment inside the habitats. Temperature extremes on Mars are severe, with daytime temperatures at the equator reaching up to 20 degrees C, 68 degrees F, and nighttime temperatures plummeting to minus 73 degrees Celsius, 100 degrees F. Habitats and spacesuits must be well insulated and capable of maintaining a stable internal temperature to protect inhabitants from these extremes. Radiation is a significant concern on Mars due to the lack of a global magnetic field and a thin atmosphere, which offer little protection from cosmic and solar radiation. Long-term exposure to high radiation levels can increase the risk of cancer and other health issues. Solutions include building habitats with thick walls, covering them with Martian soil, or situating them in natural features like lava tubes for added protection. Sustaining life on Mars requires a reliable supply of food and water. Growing food on Mars involves using hydroponics or aeroponics, which require a controlled environment and a steady supply of nutrients. Water can be sourced from subsurface ice or the atmosphere, but efficient extraction and recycling systems are necessary. Psychological challenges also play a crucial role. The isolation, confinement, and long durations of Mars missions can impact mental health. Providing psychological support, recreational activities, and communication with Earth are essential for maintaining the well-being of astronauts. Logistics and resupply are complex due to the vast distance between Earth and Mars, making it crucial to develop technologies for in situ resource utilization, ISRU. This involves using local materials to produce water, oxygen, and building materials, reducing dependence on supplies from Earth. Overall, living on Mars requires addressing a combination of environmental, technological, and psychological challenges. Successful solutions will pave the way for sustainable human presence and the potential colonization of the red planet. Colonizing Mars demands innovative technologies to ensure the survival and sustainability of human settlers in its harsh environment. These technologies span various domains, from life support systems to habitat construction and resource utilization. Life support systems. Essential for providing breathable air, these systems must efficiently produce oxygen from the Martian atmosphere, primarily composed of carbon dioxide. NASA's Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, on the Perseverance rover is a prototype demonstrating this technology. Advanced filtration systems are also needed to remove carbon dioxide and other contaminants. Habitat construction. Martian habitats must be pressurized, insulated, and shielded from radiation. Innovative construction techniques, such as 3D printing using local materials like regolith, Martian soil, can build durable structures. The European Space Agency, ESA, and NASA have explored using basalt fibers from Martian rock for construction. Energy production. Reliable energy sources are crucial for sustaining life and operations on Mars. Solar panels are a primary option, but their efficiency is reduced by dust accumulation. Small nuclear reactors like NASA's Kilo Power project offer a consistent power supply unaffected by dust storms or the planet's day-night cycle. Water extraction and recycling. Water is vital for drinking, growing food, and other life support functions. Technologies must efficiently extract water from subsurface ice or the atmosphere. Advanced recycling systems, similar to those used on the International Space Station, ISS, will minimize water waste and reduce the need for resupply missions. Food production. Growing food on Mars involves controlled environment agriculture using hydroponics or aeroponics. These methods allow plants to grow without soil, using nutrient-rich solutions. LED lighting and climate control systems will create optimal growing conditions, potentially integrating with life support systems to recycle carbon dioxide and produce oxygen. In situ resource utilization, ISRU. Technologies are critical for reducing dependence on Earth supplies. This includes producing fuel, building materials, and life support resources from Martian raw materials. For instance, extracting methane from atmospheric carbon dioxide and water can provide fuel for return missions or local energy needs. Radiation protection, shielding from cosmic and solar radiation is vital for long-term health. Solutions include building habitats underground or covering them with regolith. Advanced materials, such as hydrogen-rich plastics, offer additional protection. Transportation and mobility. Efficient transportation on Mars requires rugged, reliable vehicles for surface exploration and resource transport. Rovers like NASA's Perseverance provide a model, but scaled-up versions with pressurized cabins will be necessary for human crews. Health and medical care. Ensuring the health of settlers involves remote medical technologies, telemedicine, and autonomous systems for diagnosis and treatment. Research on the ISS provides a foundation for developing these capabilities for Mars. These technologies collectively address the fundamental challenges of living on Mars, paving the way for sustainable human colonization and opening new frontiers for exploration and discovery. Establishing a sustainable food supply is crucial for long-term human habitation on Mars. Given the harsh Martian environment, innovative agricultural methods are necessary to grow food efficiently. Hydroponics and aeroponics. These soil-less farming techniques are ideal for Mars. Hydroponics involves growing plants in nutrient-rich water solutions, while aeroponics suspends plants in the air and mists them with nutrients. Both methods can maximize yield in limited space and are well suited for controlled environments, such as Martian habitats. Greenhouse structures. Greenhouses on Mars must be pressurized and insulated to protect crops from extreme temperatures, low atmospheric pressure, and high radiation levels. Transparent materials like polycarbonate or glass, reinforced against radiation, can allow sunlight to support photosynthesis while maintaining a stable internal climate. LED lighting. Supplemental LED lighting can provide the necessary spectrum of light for plant growth when sunlight is insufficient. These lights can be optimized for different growth stages of plants, enhancing productivity. Water recycling. Efficient water use is critical. Closed-loop water recycling systems, similar to those on the International Space Station, ISS, can reclaim water from waste and condensation, ensuring a sustainable supply for irrigation. Nutrient supply. Martian soil or regolith lacks the organic nutrients necessary for plant growth. Nutrient solutions for hydroponics and aeroponics can be synthesized from Earth supplies or potentially from in-situ resource utilization, ISRU methods that extract and process local materials. Crop selection. Choosing the right crops is essential. Fast-growing, nutrient-dense plants like lettuce, spinach, and radishes are ideal for initial cultivation. Research on the ISS and Earth-based Mars simulators has shown that these crops can thrive in controlled environments. Longer-term staple crops like potatoes and wheat could be integrated into the system. Microbial support. Beneficial microbes can be introduced to support plant growth, enhance nutrient uptake, and improve soil health in greenhouse settings. These microbes play a crucial role in Earth's ecosystems and can be adapted for Martian agriculture. Automation and monitoring. Advanced sensors and automation systems can monitor and regulate growing conditions, including temperature, humidity, nutrient levels, and light. This technology reduces labor needs and ensures optimal conditions for crop growth. Waste management. Organic waste from crops can be composted and reused as a nutrient source, creating a closed-loop system. This reduces the need for external nutrient inputs and helps maintain soil fertility. Developing a reliable food supply on Mars is essential for the success of human missions and colonization. These advanced agricultural techniques and systems will ensure that astronauts have access to fresh, nutritious food, reducing reliance on resupply missions from Earth and paving the way for sustainable living on the Red Planet. Energy is crucial for sustaining human missions and potential colonization on Mars. Given the planet's harsh environment, reliable and efficient energy sources are essential for powering habitats, life support systems, transportation, and scientific equipment. Solar power. Solar panels are a primary energy source for Mars missions, converting sunlight into electricity. However, Mars receives less sunlight than Earth, and frequent dust storms can block sunlight and reduce efficiency. Advances in solar panel technology, such as dust-resistant coatings and higher-efficiency photovoltaic cells, are crucial for maximizing energy production. Deploying solar arrays in dust-free zones or using automated cleaning systems can also help maintain performance. Nuclear power. Nuclear reactors provide a consistent and reliable energy source, unaffected by dust storms or the Martian day-night cycle. NASA's Kilopower project is developing small, portable nuclear reactors that can produce 10 kilowatts of electricity continuously for years. These reactors use a uranium-235 core and passive cooling systems, making them safe and efficient for long-term missions. Energy storage. Efficient energy storage systems are vital for ensuring a continuous power supply during periods of low solar activity, such as dust storms or nighttime. Advanced batteries, such as lithium-ion or solid-state batteries, can store excess energy generated by solar panels or nuclear reactors. Thermal energy storage, which involves storing heat generated during the day and releasing it at night, is another option. Wind power. While Mars's atmosphere is thin, it still has wind that can be harnessed for energy. Wind turbines designed for the lower density of the Martian atmosphere could provide supplementary power, especially during dust storms when solar power is less effective. These turbines must be lightweight yet durable to withstand the Martian environment. Hydrogen fuel cells. Hydrogen fuel cells can generate electricity by combining hydrogen and oxygen, producing water as a byproduct. In situ resource utilization, ISRU techniques can produce hydrogen from water extracted from the Martian soil or ice. This method provides a reliable and clean energy source with the added benefit of producing potable water. In situ resource utilization, ISRU. ISRU technologies can produce energy from local resources, reducing dependence on Earth supplies. For instance, extracting methane from carbon dioxide in the Martian atmosphere using the Sabatier process can produce fuel for generators and transportation. Redundancy and hybrid systems. A combination of these energy sources, along with redundancy in energy systems, ensures a reliable and stable power supply. Hybrid systems that integrate solar, nuclear, wind, and fuel cell technologies can provide flexibility and resilience, adapting to the varying conditions on Mars. Reliable energy sources are foundational for the success of human missions and colonization on Mars. Advances in technology and ISRU will enable sustainable living and exploration, supporting the long-term goal of establishing a human presence on the Red Planet. The ethical considerations surrounding Mars colonization are complex and multifaceted, involving environmental, social, and philosophical dimensions. Ensuring that ethical guidelines are established and followed is crucial as humanity embarks on this unprecedented endeavor. Environmental ethics. Protecting the Martian environment is a primary concern. Introducing Earth life to Mars could irreversibly alter its ecosystem, potentially harming any existing Martian life forms, even microbial. Ethical colonization must prioritize thorough scientific investigation to determine whether life exists on Mars and implement measures to avoid contamination. Planetary protection. The concept of planetary protection aims to prevent biological contamination between Earth and Mars. Strict protocols for sterilizing spacecraft and habitats are necessary to avoid transferring Earth microbes to Mars, which could compromise scientific investigations and the Martian environment. Resource utilization. Ethical considerations must guide the use of Martian resources. While in situ resource utilization, ISRU, is essential for sustainability, it must be done responsibly to avoid depleting or damaging Mars' natural assets. Regulations should ensure that resource extraction is balanced with environmental preservation. Social and political ethics. The governance of Mars colonies raises questions about political and legal frameworks. Who has the right to colonize and govern Mars? International cooperation and the establishment of an inclusive governance model are crucial to prevent conflicts and ensure fair representation of diverse interests. Rights of future generations. Ethical colonization must consider the rights and needs of future generations. Ensuring sustainable practices and preserving Martian resources for future explorers and settlers is essential. Decisions made today will have long-lasting impacts on the potential for future habitation and exploration. Cultural and heritage. Preservation. Respecting Mars as a unique part of our solar system with its own geological and potentially biological history is important. Ethical guidelines should protect significant sites, such as ancient water channels or areas with potential biosignatures, from exploitation or damage. Human rights and equality. Ensuring that Mars colonies uphold human rights and equality is paramount. Access to opportunities and resources, fair treatment, and the protection of individual freedoms must be integral to the governance and operation of Martian settlements. The diverse backgrounds and needs of settlers should be recognized and respected. Philosophical considerations. Colonizing another planet prompts reflection on humanity's role in the universe. The motivations behind colonization, whether scientific exploration, survival, or economic gain, must be carefully examined. Ethical colonization should align with broader human values, promoting knowledge, cooperation, and stewardship of our cosmic neighborhood. Ethical considerations are vital to ensuring that Mars colonization is conducted responsibly, sustainably, and justly. Establishing comprehensive guidelines and fostering international cooperation will help navigate the complex ethical landscape of this monumental human endeavor. Designing habitats for Mars requires innovative architectural solutions to ensure safety, functionality, and sustainability in an environment vastly different from Earth. The unique challenges posed by the Martian environment necessitate careful consideration of various aspects. Structural integrity. Mars habitats must withstand low atmospheric pressure, temperature extremes, and potential dust storms. Structures need to be robust and resilient, using materials like high-strength composites, metals, or Martian regolith. 3D printing technology using local materials offers a sustainable and efficient construction method. Radiation protection. The lack of a protective magnetic field and thin atmosphere exposes inhabitants to harmful cosmic and solar radiation. Habitats should incorporate thick walls, regolith shielding, or be located underground or within natural features like lava tubes to provide adequate protection. Pressurization and life support. Maintaining a stable internal pressure is crucial for human survival. Advanced life support systems must provide a continuous supply of breathable air, water, and temperature regulation. These systems should recycle air and water, minimizing the need for resupply missions. Thermal regulation. Mars experiences significant temperature fluctuations, from 20 degrees C, 68 degrees F during the day, to minus 125 degrees Celsius, 193 degrees F at night. Insulation and heating systems must be efficient to maintain a stable and comfortable indoor environment. Passive solar heating and thermal mass can help mitigate temperature extremes. Modular and expandable design. Habitats should be modular and expandable to accommodate growing populations and evolving needs. Modular designs allow for the initial construction of essential living spaces, with the ability to add additional modules for laboratories, greenhouses, and recreational areas as the colony expands. Resource utilization. Utilizing local resources, in situ resource utilization, is key to sustainable settlement. This includes extracting water from subsurface ice, producing oxygen from carbon dioxide, and using regolith for construction materials. Efficient recycling systems will minimize waste and resource consumption. Greenhouses and agriculture. Integrating greenhouses within habitats is vital for food production. Controlled environment agriculture, using hydroponics or aeroponics, can provide a steady supply of fresh food while also contributing to air purification and humidity control. Habitability and comfort. Ensuring the well-being of inhabitants requires attention to psychological and social needs. Habitats should provide private living spaces, communal areas, recreational facilities, and access to natural light. Designing aesthetically pleasing and functional interiors can improve morale and mental health. Transportation and mobility. Efficient transportation systems within and between settlements are necessary for mobility and resource transport. Pressurized rovers and tunnels can facilitate safe movement across the Martian surface. Safety and redundancy. Redundant systems for life support, power, and communication are essential to ensure continuous operation in case of failures. Emergency shelters and protocols should be in place to handle potential hazards like equipment malfunctions or environmental threats. Mars settlement architecture combines engineering, sustainability, and human-centric design to create habitable environments that support long-term human presence. By addressing these aspects, architects and engineers can develop resilient and adaptable habitats for future Martian colonists. Living on Mars poses significant health risks due to the planet's harsh environment and isolation from Earth. Addressing these risks is crucial for the success and well-being of future Martian settlers. Radiation exposure. Mars' thin atmosphere and lack of a magnetic field offer little protection from cosmic and solar radiation. Prolonged exposure increases the risk of cancer, neurological damage, and other health issues. Effective shielding, such as habitats covered with regolith or built underground, is essential to minimize radiation exposure. Reduced gravity. Mars' gravity is about 38% of Earth's, which can lead to muscle atrophy, bone density loss, and cardiovascular deconditioning. Regular exercise regimes and resistance training are necessary to mitigate these effects. Research into artificial gravity solutions, such as rotating habitats, could provide long-term solutions. Psychological challenges. The isolation, confinement, and distance from Earth can cause psychological stress, depression, and anxiety. Providing mental health support, recreational activities, and maintaining communication with Earth are vital for psychological well-being. Designing habitats with private spaces and communal areas can also help reduce stress. Limited medical care. The lack of immediate access to advanced medical facilities presents a significant challenge. Astronauts will need to be trained in emergency medical procedures, and habitats must be equipped with medical supplies and diagnostic tools. Telemedicine, supported by communication with Earth-based doctors, can provide remote medical assistance. Radiation-induced illnesses. Beyond cancer, radiation can cause acute radiation syndrome, damage to internal organs, and impaired immune function. Monitoring radiation levels and implementing protective measures are crucial for preventing radiation-induced illnesses. Nutritional deficiencies. Maintaining a balanced diet on Mars is challenging. Reliance on hydroponic or aeroponic agriculture and stored food can lead to nutritional deficiencies. Ensuring a diverse crop selection and supplementing diets with necessary vitamins and minerals is essential. Immune system changes. Space travel and the Martian environment can weaken the immune system, increasing susceptibility to infections. Strict hygiene protocols, regular health monitoring, and a robust medical response plan are necessary to manage health risks. Environmental hazards. Martian dust, composed of fine particles, can pose respiratory risks and affect equipment. Effective air filtration systems and dust management strategies are necessary to protect inhabitants from respiratory issues and equipment malfunctions. Injuries and accidents. The unfamiliar environment and the potential for equipment failures increase the risk of injuries and accidents. Training in emergency response, maintaining safety protocols, and having redundant systems can help manage these risks. Long-term health effects. The long-term health effects of living on Mars are still unknown. Continuous health monitoring, research, and adaptation of medical protocols will be necessary to understand and mitigate these effects. Addressing these health risks requires comprehensive planning, robust infrastructure, and ongoing research to ensure the safety and well-being of Martian settlers. Mars missions pose unique psychological challenges due to the extreme isolation, confinement, and distance from Earth. Addressing these challenges is critical for the mental health and well-being of astronauts and future Martian settlers. Isolation. Mars missions involve long durations with minimal contact with Earth, leading to feelings of loneliness and isolation. Effective communication systems that allow for regular contact with family and support networks on Earth are essential. Virtual reality tools can also help simulate Earth-like environments and social interactions. Confinement. Living in confined spaces for extended periods can lead to stress, irritability, and conflicts among crew members. Habitat design should prioritize private spaces, communal areas, and recreational facilities to provide a balance between solitude and social interaction. Regular physical exercise can also help alleviate stress and improve mental health. Distance from Earth. The vast distance to Mars, with communication delays of up to 24 minutes, can exacerbate feelings of isolation and anxiety. Developing autonomous systems and decision-making protocols can empower astronauts to handle situations independently, reducing stress related to delayed communication with mission control. Monotony and routine. The repetitive nature of daily tasks can lead to boredom and reduced motivation. Providing varied activities, opportunities for personal growth and creative outlets can help maintain mental engagement. Scheduled leisure activities, hobbies, and entertainment are also important for psychological well-being. Team dynamics, close quarters living and working can strain interpersonal relationships. Crew selection should consider psychological compatibility and conflict resolution skills. Regular team-building exercises and counseling support can enhance cohesion and cooperation. Stress and anxiety. The high-stakes environment of Mars missions can induce stress and anxiety. Training in stress management techniques, mindfulness, and relaxation exercises can equip astronauts to cope with pressure. Access to mental health professionals through telemedicine can provide additional support. Sleep disruption, the Martian day, or SOL, is approximately 24.6 hours, slightly longer than an Earth day. Maintaining a consistent sleep schedule and creating a conducive sleep environment are crucial to avoid circadian rhythm disruptions, which can affect mood and cognitive function. Cultural and social factors. Diverse backgrounds and cultural differences among crew members can lead to misunderstandings and conflicts. Promoting cultural awareness and inclusivity within the team can enhance mutual respect and understanding. Coping with emergencies. The potential for emergencies and the inability to return to Earth quickly can create anxiety. Comprehensive training in emergency response, robust safety protocols, and psychological support systems are essential for managing these fears. Addressing these psychological challenges requires a multifaceted approach, integrating habitat design, support systems, training, and continuous monitoring. By prioritizing mental health, Mars missions can ensure the well-being and productivity of astronauts, paving the way for successful long-term habitation. Mars moons, Phobos and Deimos, are small, irregularly shaped bodies that offer intriguing opportunities for scientific research and exploration. Their characteristics and origins provide insights into the Martian system and the broader processes of moon formation and planetary science. Phobos. The larger of the two moons, Phobos is about 22 kilometers in diameter. It orbits Mars at a distance of approximately 6,000 kilometers, closer than any other moon to its planet in the solar system. Phobos's proximity to Mars results in a rapid orbital period, completing a circuit around Mars in just 7.65 hours. This close orbit is gradually decaying, and Phobos is expected to either crash into Mars or break apart and form a ring within the next 30 to 50 million years. Phobos's surface is covered in a thick layer of regolith, which suggests significant impact activity. Deimos. Deimos is smaller, with a diameter of about 12 kilometers, and orbits Mars at a distance of approximately 23,500 kilometers. It has a longer orbital period, taking about 30.3 hours to orbit Mars. Deimos appears smoother than Phobos due to a thick layer of regolith that fills its craters. Origin. The origins of Phobos and Deimos are debated. One hypothesis suggests they are captured asteroids from the nearby asteroid belt, due to their irregular shapes and similarities in composition to carbonaceous chondrite asteroids. Another theory proposes that they formed from debris ejected by a massive impact on Mars. Understanding their origin can shed light on the history of the Martian system. Exploration. Missions to Phobos and Deimos can provide valuable scientific data. The Japan Aerospace Exploration Agency, JAXA, is planning the Martian Moons Exploration (MMX) mission to study these moons, aiming to land on Phobos, collect samples, and return them to Earth. Exploring these moons can reveal their composition, structure, and the potential for future resource utilization, such as mining for water or other materials. Scientific importance. Studying Phobos and Deimos can help scientists understand the processes that shape small bodies in the solar system. Their surfaces are likely rich in carbonaceous material, which could offer clues about the early solar system and the building blocks of life. Strategic value. Phobos and Deimos could serve as bases for future Mars exploration missions. Their low gravity makes landing and takeoff relatively easy, and they could provide staging points for robotic or human missions to Mars, offering a place to store supplies or refuel spacecraft. Phobos and Deimos, though small, hold significant scientific and strategic value for the exploration of Mars and the broader solar system. Their study can enhance our understanding of planetary formation, the history of the Martian system, and the potential for future human exploration. The future of Mars exploration is poised to be one of the most ambitious and transformative endeavors in human history. Building on decades of robotic missions, the next steps aim to achieve human presence and sustainable operations on the Red Planet. Robotic missions. Robotic missions will continue to play a critical role in Mars exploration. NASA's Perseverance rover is currently searching for signs of past life and collecting samples for future return to Earth. The European Space Agency, ESA, and Russia's Roscosmos ExoMars mission, set to launch in the coming years, will further explore the planet's geology and search for biosignatures. Sample return missions. NASA and ESA are planning the Mars Sample Return mission, which aims to bring Martian soil and rock samples back to Earth for detailed analysis. These samples will provide invaluable insights into Mars's geology and potential for past life, helping to inform future human missions. Human missions. NASA's Artemis program, aiming for a return to the Moon, is seen as a stepping stone to Mars. The experience gained from lunar missions will help develop technologies and strategies for Mars. SpaceX's Starship, designed for deep space travel, is a key player, with plans to send humans to Mars in the 2020s infrastructure development. Establishing a sustainable presence on Mars requires significant infrastructure development. This includes habitats with life support systems, power generation facilities using solar or nuclear energy, and in situ resource utilization, ISRU, to extract water and produce oxygen and fuel from Martian resources. International collaboration. The complexity and cost of Mars exploration necessitate international cooperation. Agencies like NASA, ESA, Roscosmos, and private companies like SpaceX are collaborating to pool resources and expertise, making Mars missions more feasible. Scientific research. Ongoing and future missions will focus on understanding Mars' climate, geology, and potential for life. Research into Martian dust, atmosphere, and water ice is crucial for planning human missions and ensuring the safety and sustainability of long-term exploration. Ethical considerations. The ethical implications of human activity on Mars must be addressed. This includes preventing biological contamination, protecting potential Martian ecosystems, and considering the long-term impacts of human presence on the planet. Technological innovation. Mars exploration drives technological advancements in robotics, artificial intelligence, autonomous systems, and human life support. These innovations not only benefit space exploration, but also have applications on Earth in areas such as environmental monitoring and remote operations. Public engagement. Inspiring and engaging the public is vital for sustaining support for Mars exploration. Education and outreach programs, along with media coverage and science fiction, help cultivate interest and excitement about the Red Planet. The future of Mars exploration promises to push the boundaries of human capability, offering profound scientific discoveries and paving the way for humanity's expansion into the solar system.